part of the notes for 4.4, derivatives of exponential and logarithmic functions. So we've done 3 of the 4 formulas so far. This is the 4th one. This is for a logarithm that does not have a base of e. So I don't know if you recall whenever you learned about logarithms, ln of x is really log base e of x. So anytime you have a logarithm of base e, you're going to follow the derivative for the natural log. But if your base is something else, like for example in a, like we have here, you're going to use this formula. Again, it's identical. The only difference is this natural log of a that's in the denominator. And again, we didn't need it for the natural log because natural log of e is simply 1, so it didn't really make sense to include that. So 4th formula, you have 4 of those new formulas to learn. Again, 1 over u times natural log a is the base, u is kind of what you're taking the logarithm of, and then times the derivative of u. Okay, so then we have this interesting example. We're finding the derivative if y is equal to the log base a of a to the sine of x power. And this is going to be an example of why it's important to simplify using your logarithm rules before you do any type of derivative process. So I'm going to work this out the traditional way first, and then go back and show you a shortcut. So if we are taking the derivative of this, the very first thing you want to do is do 1 over what you're taking the logarithm of, so a to the sine of x, times the natural log of a, because again, a is my base there. And then I'm going to multiply that by the derivative of what I'm taking the exponent of. And this does include the chain rule. So the derivative of an exponential, I repeat what I have, times the natural log of the base, times the derivative of the exponent, which is going to be cosine of x. So if we go through and look at this, we have a to the sine x, a to the sine x, natural log a, and all that I'm left with is cosine of x. So the derivative of this complicated looking logarithm is merely cosine of x. Now, if we look at this original problem, if you recall from your rules of logarithms, anytime you have an exponent with this logarithm, you can actually bring that out front. So this is the same thing as sine of x times log base a of a. And also, if you recall, anytime you have a logarithm where your base and what you're taking the log of match, that's equal to 1. So this is really sine of x, because this entire quantity is 1. So this complicated logarithm equation is really just the same thing as saying that y is equal to sine of x. And then when you take the derivative of that, of course, the derivative of sine of x is cosine of x. So we get the same thing. That's why it's important to always simplify before you take a derivative. Okay, lastly, this is an additional rule. It is the last time you're going to see something new with the power rule, and this is for any arbitrary real power. So the rule looks the same, the proof is different, which is why it has a different rule number than what we've looked at before. And in this one, n could be any number at all. So we looked at positive integers, we looked at negative integers, we looked at rational exponents, and now we're looking at all real power integers. All real power exponents. So you could have exponents that are pi, you could have exponents that are irrational, like square roots, anything like that. And this is what I mean by that. So we have 2 different questions here where we're finding the derivative. Over here, find the derivative of x to the square root of 2 power. Again, I'm going to do this just like I did with the traditional x to the 3rd power. The derivative is going to be bring the exponent down in front as a coefficient. Then you do x, and then you're going to subtract 1 from the exponent. So that's going to be to the square root of 2 minus 1 power. I can't do anything else with that. I can't simplify that. So that would actually be your correct answer there. Okay, part B. This one we do have to use the chain rule. I have to deal with the pi as an exponent first, and then I'll have to actually take the derivative of the inside. Remember, using the chain rule, you don't want to do too much at once, so you want to make sure you deal with the entire quantity and then deal with what's on the inside. So this is going to be pi times 2 plus sine of 3x to the pi minus 1 power, and then I'm multiplying by the derivative of the inside. Well, the derivative of the inside is going to be 0 plus cosine of 3x, and then I have to multiply by the inside of the inside, so the derivative of the 3x would be times 3. So putting this all together, I can kind of drop this 0 plus. I'm going to have a 3 times a pi, so I'm going to have a 3 pi out in front. I'm going to have a cosine of 3x out in front, and then I have 2 plus sine of 3x to the pi minus 1 power. So chain rule, got to make sure that you follow that there. Make sure you don't leave any parts out of your answer. Okay. So example 6, we have if f of x is equal to the natural log of x minus 3, find f prime and state the domain of f prime. Well, the domain of the original is going to be 3 to infinity. Notice 3 is not included, so we could plug in anything that is greater than 3 into the original problem. The derivative is 1 over x minus 3 times 1, which is 1 over x minus 3. Well, obviously x can't equal 3, and even though on its own we could plug in things like 2 and 1 and 0 into this f prime, because of the original domain, the domain of the derivative cannot add values in that weren't in the original constrictions. You can take values out, and in some cases, numbers are included in the original and they're not included in the derivative, but you cannot add them back in. So the domain here is still 3 to infinity, even though technically it would be possible to plug in things like 2 and 1 and 0 on its own. But because it was a derivative, we have to go by what the original domain was. Again, we can continue to take values away, but we cannot add values back into the domain of the derivative. So if we look at the graph of this, we plug in 4, that's going to give us 1. You do have an asymptote here at 3. So it's not actually going to be passing through 3. 3.5, so that's 1 divided by 0.5, that's going to be 2. If I plug in 5, I'm going to get 1/2. And so you're actually going to be this. So instead of having both sides of this rational function, we only have one side of it. We're only going to have the right-hand side. Okay, now we're looking at an interesting question. These ones used to appear on AP exams quite frequently, but I haven't actually seen one for a while. However, I want to make sure you guys know how to deal with this. You can't take the derivative of this question as is because of the x to the x, because it's not a power rule, it's not an exponential, because you have variables in both parts of that. So the only thing we can do here is rewrite it so that there's no more variables in the exponent. And we can do that by taking a natural log. Because when I do that, I can use the exponential rule and bring that x down so that it's in front. Now we can go through and take the derivative with respect to x. We would have to do implicit differentiation on the y. So I'm going to do my d dx on the entire quantity. So on the left-hand side, the derivative of natural log y is 1 over y times the derivative of y, which is dy dx. On the right-hand side, I have to use the product rule. So that's the first times the derivative of the second, and then times 1, because the derivative of x is 1, plus the second times the derivative of the first. So I have 1 over y times dy dx is equal to 1 plus natural log of x, and then to get rid of this 1 over y to solve for the derivative, I would multiply both sides by y. So your derivative is going to equal exactly what we have here. You can distribute, you don't have to. But there is a substitution we can do here at the end to get a derivative that is just in terms of x. If you notice here, we have this y, and I know what y is equal to. According to the original problem, y was equal to x to the x. So my derivative here, instead of being y times this, it's going to be x to the x times 1 plus natural log of x. So again, we have to go back and do that substitution there at the end. There is one more example that's in your book, and I'm not actually going to go over it because it's not something I'm going to focus on, but I do want you to look over it in your book. I think the book's video does go through this, which it's interesting because this deals with the spread of a flu. Notice that they give you this equation and it has an exponential in it. That's why it fits into this formula. So this is something I do want you to go over and check out, but it is not something I'm actually going to go through with this video. If you do have additional questions on this, please ask me and I can answer those. Otherwise, go back, rewatch this video, rewatch the first video, and reach out to me if you have any questions at all.